And we're live. Yes. Excellent. Woo. Fantastic. Okay. Giving people an opportunity to get into the chat. Let me fill you guys in on a few things that are coming up in the future. Something that may or may not affect you. It's kind of up in the air at the moment. The other week, I was out for the vaccine shot, and I'm supposed to be getting another, my second dose, I guess, on the 17th, which is an A day, which does not affect you guys. But as I've mentioned in the past, people have told me that they get the second shot and they get, basically, it feels like a punch to the face. So they were telling people, friends have been telling me, hey, you might consider taking that another day off. And I'm like, I don't want to take another day off. Why can't I just come in and do my job? But so just a heads up that, in the next couple of weeks, I may have another day out. But of course, you have your Chromebook, so, things will get done regardless. Next, the date that was settled upon based on, remember the survey that you guys filled out for me for AP Stat Preference? The date that was settled upon, we settled upon the second testing window. I can't recall off the top of my head what the second testing window was. I believe it was in that survey. In fact, I could probably find that right here. Yeah, there it is. Instructions to the form. There we go. The second testing window was May 25th. May 25th. So we have until May 25th, which basically it buys us an extra week, basically, of reviewing. They're trying to spread out the AP testing a little bit more amongst the individual AP classes. I think this is definitely a positive. The 25th, when is Memorial Day? My goodness, hold on a tick. May, oh, good. It's before Memorial Day. You know how like Memorial Day weekend, you usually get that Monday off? They actually, what they've done in the past, do you guys remember what they've done in the past with your snow days? With Memorial Day weekend? No? Okay, cool. Memorial Day weekend, I think they're going to do it this year. Don't quote me on that, but Memorial Day weekend, I think they're going to take your 2 snow days that we never used and put them on that Thursday, Friday before Memorial Day. So it's possible you might get a 5-day weekend. That still will not affect us in terms of the AP test. Tuesday, May 25th, as far as I can see, that is the date of our AP test. So, yeah, excitement fills the air. Cool. Finally, you did have something due for me today. I haven't looked at any of them yet. I'm just kind of skimming through it right now. I should have those graded fairly quickly, hopefully fairly quickly. I got very delayed with grading in the last couple of weeks, mainly because I was out for that one day, and then I was still trying to catch up ever since. So, for those in the chat, I see 11 people in the chat right now. If you would, please leave a comment for me in that chat. That would be much appreciated, so I could have that for my records. Wonderful, wonderful. There come some more comments chiming in. Okay. We're going to be taking another step forward with hypothesis testing. I mentioned when we first started touching upon hypothesis testing that like hypothesis testing is a huge deal. It's a big deal. It's something that we're going to continue working on pretty much all the way through to the AP test, whether it be one proportion hypothesis testing, which is what we've done, to regular Z testing or T testing or chi-squared testing. Everything is going to come down to hypothesis testing. It's going to be wonderful. Today, I take another step forward with that. So if you would, ladies and gentlemen, if you do not already have them out, I'm going to need those notebooks out and open. I do a little wave now with that. That's pretty cool. My little wave is kind of like signifying the opening of the notebooks, I guess. I don't know. It's a little weird. Did you find the episode? That's okay. Again, this is a show that's like 50 something years. My dad was on the show 50 years ago. Think about that. My goodness. My dad's a bit older than other people's dads. It's weird. When I was born, my dad was 44. 44. Some of your parents right now might be 44, right? Yeah, think about that. When my dad was 44, I was born. Like, I don't know. It's just, it can happen. It can totally happen. But now it's like, when most people my age, they're like, oh yeah, my dad, he just retired. He turned 60, blah, blah, blah. Kids my age are saying, oh my dad's like 60, blah, blah, blah. Like, yeah, my dad's 82. My dad was born when World War II was still a thing. 1939. My word. Anywho. Okay. Before I get into the details of the hypothesis testing that I want to talk about today, I want to draw a little chart for you. Now, this chart, I'm not going to give it a title. I'm not going to give it a title in our notes, simply because it doesn't really fit in with any one section. I'll give you a title with the next thing that we do, the next part that we do. But I just want to draw this little chart for you, just as kind of a helpful thing. The question that I kind of give to this chart is, which hypothesis test do I use? Question mark. And then here's a face who's like, what? What do I use? That's the face that the dude's making right there. I should get the the chat open on my phone. But anyway, when it comes to typical hypothesis testing, a lot of it comes down to either Z testing or T testing. What we did last week, in the past week and so, with proportion testing, technically that was Z testing. Z testing is anything that eventually uses normal CDF. Z testing, Z scores, the normal curve. Anytime you hear the word Z testing or Z or anything like that, I need you to be thinking normal curve. Either it's going to come down to Z testing or a test that we haven't talked about yet, T testing, which I'm not going to get into the details of at all today. I just wanted to give you this little chart. Eventually, like I said, it is going to get into chi-square testing, which doesn't fit into this chart, but that's a very, very precise situation, which I will get into. So here's the question. Test. The first question that you need to ask yourself in terms of the test that you are going to perform, do you have categorical data or do you have quantitative data? This is the first big question that you need to be asking yourself, because when it comes down to these questions about hypothesis testing, they're not just going to spoon feed you all of the information. You are going to have to make a wise decision on your own based on the context of the question. So the first thing that you need to kind of put in the back of your mind is, what type of data are they talking about? Quantitative data, as we've talked about in the past, it makes sense to take an average of. Categorical data, typically categorical data is expressed through proportions, percentages. I say typically percentages because obviously there are some certain exceptions to that rule, but that's for a future date. Typically, if you're dealing with proportions, you're dealing with categorical data. We did a problem on an assessment that dealt with like moths, I believe it was. I think it was moths or something like that. I'm trying to recall what it was now. I'm going to get the wording of this thing. Hold on. I'm going to get the wording of this thing, because I want to bring it up for a very, very specific reason in regards to categorical versus quantitative data. And it's right here. There it is. Cool. Flip my screen. Boom. There it is. Gypsy moth. I'll read this question just because I want to talk about the categorical quantitative data conundrum before we continue with this. The gypsy moth is a to oaks and aspen trees. The state agricultural department places traps throughout the state to detect the moths. Each month, a simple random sample of 40 traps is inspected. The number of moths in each trap is recorded. Time out for a second. The number of moths in each trap is recorded. Right off the bat, is that categorical or quantitative? It's quantitative. Yeah, it's quantitative. But continue for a second. And the mean number of moths is calculated. Based on years of data, the distribution of moth counts is discrete and strongly skewed with a mean of 0.45 and a standard deviation of 0.62. The distribution of moth counts, the number of moths, 0.45. Some people looked at this question, and it was kind of designed to kind of not mess with you, but to really make you think about what type of data you have. Because when they saw 0.45, people interpreted that as 45%. And they immediately went forward with some of the proportion calculations that they did. And I was like, ooh, this isn't categorical data. This is not proportions. That 0.45 doesn't represent 45%. It represents 0.45 on average moths found within each of these traps. So just, we have to look into the context in order to determine categorical or quantitative. So back to this, because then your decision as to which test you're going to use becomes a little bit clearer. If you have categorical data, typically you are dealing with proportions. I'm going to have to extend this page a little bit. That's okay. There we go. You are dealing with proportions. And if that is the case, then typically you have something like a p hat, like a sample, something along those lines. If that is the case, then you are going to be using a z-test, no matter what. You are going to be using a z-test. Could it be a 1 proportion z-test? Could it be a 2 proportion z-test? I don't know. But you will end up using a z-test. You will end up using normal CDF at some point. Could be something on your calculator, which I'm going to bring up the calculator in a moment just to kind of show you. But that's what you should be doing. Now, if I go to the calculator, just to be very clear about this, I've shown you where these tests are. If you hit stat and go over to tests. Now, yes, the first one is what is known as the z-test. That is not, I don't like the way they label things in here, because then if you go down a little bit farther, look right there, this is a 1 proportion z-test. They're both z-tests, except number 5 is the one that you would use for proportions. Number 1, you're not going to touch that for proportions. You're going to touch that when you get to quantitative data. I'll talk about that in a moment. But if you go down to 1 prop z test, this is where you would put in your null hypothesis and your x and your n, which the x and the n would demonstrate the p hat. That would be your sample. Now, if I go over to regular z-test, there is no spot for me to put in a proportion. There's no spot for me to put in a proportion if I go to regular z-test. In fact, if I go to regular z-test, look at the symbol. I know this is a little weird because it's the calculator's version of it, but what is that? It's mu. Yeah, it's mu. Mu is, again, the population parameter for quantitative data. And again, calculator, what is that? Standard deviation. Would you remember the name of the symbol? Sigma. It's sigma, yeah. But again, this is for quantitative data. This is dealing with means. This is dealing with when it makes sense to take an average of something. And you're going to be going through a bunch of these tests in the next several weeks and months. And I just want you to get used to what these interfaces typically look like. As a side note, the input option that they give you, you can either put it in as data or stats, which is weird. But the reason why they give you data is because they're like, oh, you have data entered in L1 and you want to run a test? Yeah, we typically don't do that. Typically, we just go over to stat, and it kind of changes that stuff up on us. And now all of a sudden, oh, look, there's our sample average. There is our, number of trials or whatever it was, sample size, things like that. Anywho, back to this. So now that we talked about categorical data, if you have categorical data, boom, z-test. What type of z-test? Well, that depends. That depends on how many samples you have. That depends on the context of the problem. We'll deal with that. If you have quantitative data, that means that you have means. It means that you've taken an average of something. It means that you have some kind of an X bar, a sample average. This actually splits into two scenarios. This splits into two scenarios. And this scenario is going to be huge. This scenario is going to depend on whether or not you have sigma or you don't have sigma. Should draw that a little bigger. There we go. Or zoom in on it. That'd probably be good too. I'll just zoom in on the categorical side of the quantitative side of this, and then I'll zoom out later. The question is, do you have sigma or you don't have sigma? Typically speaking, in real life, it is very rare that you have this. Very rare. It is not likely in real life that you're going to have this. But you may have some problems, a bunch of free response questions, multiple choice questions, that basically say, let sigma equal this. And if they tell you to let sigma equal this, boom, you have sigma. You have the population standard deviation. It's very rare that you would actually have that, in real life, but these problems just kind of offer you that information. If they don't offer you that information, if they don't tell you what the population sigma is, you're not allowed to assume what it is for quantitative data. For categorical data, that's a different story. We'll deal with that in a different way. Obviously, we can calculate the standard deviation to be the square root of PQ over N. But for quantitative data, we don't have proportions, and we can't do that calculation. Typically, the calculation that we would do to find the standard error, per se, would be sigma over the square root of N, but we would still need sigma. We would still need that sigma. If you have that sigma, then you would be running, I'll move it up, you would be running a z-test. Again, a z-test. And I'll show you on the calculator the difference for when I select z-test versus t-test. Because if you don't have sigma, then you would be running a t-test. The reason why they call them z-tests is because of that normal curve being able to be expressed using z-scores. The reason why they call them t-tests is literally because that's just what the guy chose to call it. It's actually a very interesting story about how this guy came up with t-testing. It actually involves taste testing beer. But that's a story for another day when we actually get into t-testing. So, well, I'll tell you one short part of it. What is one of the conditions for, what is one of the conditions for z-testing in terms of your sample size? What? Less than 10% of the population. What else about the sample size, though? If you're doing proportions. But what about the sample size? Yeah? Large enough. Large enough. Now imagine that you are a guy who is responsible for the quality of alcohol at a brewery. How do you determine the quality of the alcohol at the brewery? Well, you have to taste it. You have to sample it. Well, if you're the guy who is responsible for taste testing the beer at a brewery, are you really going to have a sample size that is quote unquote large enough? Because you will be passed out by the end of the day. That's a fair statement, I would think. T-testing is for when, number one, you don't have the population standard deviation, but with T-testing, your sample size does not need to be, quote unquote, large enough. Doesn't have to be. Anyway, back to this. Let me show you the calculator one more time for this. Zooming in, zooming in, zooming in, zooming in, zooming in. Anyway, but that's not the only story behind it. It's actually a much more interesting story. So the first two options for testing, you can see right here, the first two options are z-test and t-test. If I go into z, there is an option right there for sigma. There's an option for you to put in sigma, because if you're doing the z-test and quantitative data, they're running with the assumption that you have it. You have the population sigma. But if you go over to t-test, all of a sudden, that option to type in sigma is gone. Because if you're doing a t-test, they're running with the assumption that you do not have the population standard deviation. That is literally the definitive action that you have to make in determining quantitative data, Z versus T. Which one do I use? Well, do you have the population standard deviation? And if you do, you go ahead with Z. It works a lot. It works the same way with other things. So for example, two sample Z right there. There are multiple spots to put in sigma right there. Sigma 1, sigma 2. That's two sample Z. But when you go two sample T, there's no spots for sigma whatsoever. So I believe you have a similar interface on your calculators to this one right here. It was just faster for me to use this one. So by the end of this, we're going to be using all of these tests right here, the top 6. We're going to be doing, well, we've done one proportion Z interval. We're going to be doing other intervals as well. And right there, there's chi-squared. We're going to be doing chi-squared as well. Hopefully at some point. We'll see. The rest of them down here, we don't really use. We don't use these bottom 3 at all. Although I think you do have a couple more in your calculator. But that's neither here nor there. Okay. Put this over here. And let's actually get into the official lesson for the day. I wanted to make sure you had that chart, though. Let me just review it one more time, just for the sake of argument, obviously. Zooming out, zooming out, zooming out. Which test do you use? Well, do you have categorical data or do you have quantitative data? If you have categorical data, pretty much you're going to be using a Z test. Oh no, it fell again. If you have quantitative data, well, which test do you use? It depends on whether or not you have the population standard deviation. Eventually, we're going to see a lot of examples like that, and that chart should be popping up in our minds in terms of, well, which test do I use? Because I have a bunch to choose from. So far, you've only been taught about one of these tests. You've only been taught about a one sample proportion test. Well, today we're going to be talking about a 2 sample proportion test / interval. I'm going to be talking to you about 2 sample proportion intervals as well. Today is the 8th. Here we go. Boom. Okay. I'm going to go on kind of a weird example. This is an example that was done through the textbook through one of these sample problems. But let me just set up the scenario. So here is the example. Here's the example. 2 separate samples were taken. Now, mind you, I say 2 separate samples were taken. There's independence between the 2 samples. They're separated from one another. Let's just assume independence in that sense. They recorded whether or not a baby had a low birth weight. Now, there are a number of reasons as to why a baby would have a low birth rate. Weight, I should say. If typically people think about the baby being born too early. If the baby's born too early, then sometimes they have a low birth weight and they have to stay in what is known as a NICU for a little while in order to gain that weight in order to be strong enough to be able to go home. Other times, they are potentially born with certain anomalies that cause them to have low birth weight. Sometimes it's genetic. Sometimes it's actions that the parents have taken, whether it be like a narcotics use or something along those lines. There's a whole bunch of different reasons, but that's not the point. The point of this is that there were 2 samples taken in New York City within a few years of the events of 9/11. Now, it seems weird for me to say, but understand that this actually is a very serious topic. Now, notice I split my paper right here. There was a random sample of 182 babies born near the 9/11 site. Now, when I say near the 9/11 site, I mean not so much that the hospital was near the 9/11 site, but the parents, the mom and dad, they lived near the 9/11 site, within a certain distance of the 9/11 site. Let's say within a certain number of miles. 8% had low birth weight. There was another random sample. I said there were 2 separate samples taken. There was another random sample of 2,300 babies not born near 9/11 site. 4% had low birth weight. So the scenario is they are both random samples. We do not know what the population parameter is whatsoever. There is no claim as to whether, as to what the population parameter could be. These are just 2 random samples. Move this up a bit right here. There we go. It's interesting. I was talking to somebody the other day about events that happened during our lives. And because obviously your generation, the event that is clearly happening at the moment is you're living through a pandemic, which is like, wow, once in a lifetime opportunity. When I was a senior in high school is when 9/11 actually happened. I was a week or two into the school year or something like that when 9/11 happened. And I was like, wow, what a bookend to my high school career. Because 9/11 happened my senior year. You know what happened my freshman year? Columbine. Yeah, no joke. Like, wow, what a change, you know. But it's like, now, what does your generation have? Oh, well, we lived through a pandemic. Wow. It just, yeah, life just sometimes punches you in the face like a second vaccine. Anyway, here's the question. Does this indicate that exposure to the debris of 9/11 led to more low birth weights? That is the main question. Does this indicate that exposure to the debris of 9/11 led to more birth weights? Or more birth weights. I wrote it correctly on the paper. Led to more low birth weights. This is a real thing. You guys know Officer Tater? In the school, you know Officer Tater? You don't know him? Okay, cool. He's one of the older security guard guys. He walks around, super nice guy. Like 9/11 happened, he drove straight up to the site, like on the day. The dude was a first responder. He's fantastic. I know a lot of guys who were in this area, obviously, who did that kind of thing. They went straight to the site when the thing happened. It's crazy to think the long lasting effects that 9/11 had. For example, just as a side note, I have a cousin who her husband was a NYPD. Now he was a first responder on 9/11. He survived. He was a first responder on 9/11. He was there for all of it. He was there, cleaning up as much as he could, finding as many, people as he could. And then, life moved on. And it was, I want to say 4 or 5 years ago, he developed lung cancer as a result of what he inhaled when they were cleaning up during 9/11. And he eventually died. And it was the official cause is basically injuries sustained from the 9/11 attacks. It's crazy, but it's never in the official numbers of as people have died. But it literally was. It's insane to think about that. And now you have the possibility of low birth weight in babies, and low birth weight in babies is sometimes can be a life and death situation. It's a very serious kind of topic. Not to put a downer on the morning. But you have one random sample of 182 babies who were born near the 9/11 site, and you have a random sample of 2,300 babies not born near the 9/11 site. There's obviously a large difference in the sample size. That is okay. For a few different reasons. Number one, both sample sizes are large enough. But more importantly, you got to think about babies born near the 9/11 site within the parents were living within a few miles of the site and possibly inhaled some of that debris and soot and ash and things of that nature that could have affected this baby's birth weight. There are not that many in the population compared to the rest of the population of babies in America. So if you're trying to be within that 10% rule, your sample size has to be less than 10%. Well, you have to do it both ways. 182 is less than 10% of all babies born near the 9/11 site or who could have been affected, their parents breathing in the soot and ash and whatnot, versus 2,300 babies being less than 10% of all babies in the United States not born near the 9/11 site. So these conditions, that's Officer Tater, by the way, if you didn't see him. He literally just walked by. Okay. He's not in my imagination, I think. Anyway, all of these assumptions, conditions apply, but you have to double it. You kind of have to double it. You have to do assumptions and conditions for both random samples. What was okay, so large enough sample size, less than 10%. What was one of the other ones that you guys mentioned about sample size? Success failure. You have to do, now you can't do expected. You can't do expected because there is no population parameter. There is no population parameter, but you still have to do successes and failures, but now you can't do expected, you have to do observed. So you have to talk about observed successes and failures. So in this, and again, I say successes and failures not in terms of good and bad, but in terms of what we're looking for. But you would do 182 times 0.08 and 182 times 0.92 to show that both are greater than 10. Same thing for the 2300. You would have to do all of that. Random sample for both. Independence that can be assumed. Not only within the sample itself, but an additional independence between between samples. Basically, it's almost exactly the same thing. It's a bit more writing and it's a bit more work and it's a bit more legwork to kind of finally get to that point where you can actually perform the test. So let's walk through it. Let's walk through it a step at a time. Let's walk through the hypothesis test, the 4 steps that we have to do. Number 1, we have to state our hypotheses. Number 2, we're going to have to go with assumptions conditions in order to show what test we're going to use. 3, we're actually going to perform the test and we're going to get a p-value. And then 4, we're going to come to a conclusion based on the evidence that we've put together. Ultimately, answering this question: do we have evidence to show that the debris of 9/11 led to more low birth weights? Now, clearly looking at the evidence here, well, this was 8% and that was 4%. I understand that. I understand that the 8% is greater than 4%. Yes. But is this enough evidence to show for all babies born near and not near the site? How do we actually go about doing that? Number 1, hypotheses. Step 1, hypotheses. We're going to have to talk about a null hypothesis and an alternate hypothesis. Null hypothesis, there's nothing going on. Null hypothesis, innocent until proven guilty. Null hypothesis, nothing out of the ordinary. How the heck do we verbalize a null hypothesis for this situation? How do we verbalize a null hypothesis in context? Think about the general idea behind null hypothesis. Again, what I mentioned before. Null hypothesis, there's nothing going on, nothing out of the ordinary. How do I express that for this problem? Ooh. I'm trying to show whether or not there were more low birth weights for babies born near 9/11, or the 9/11 site, I should say. But the null hypothesis is nothing going on here. What does that mean? Ooh. What does that mean in terms of the difference in birth weights? Yeah? It's not significant enough. Or put it in more blunt terms. More blunt terms, because yeah. I'll say it like this. You say it's not significant enough. I'm going to say this: null hypothesis. There's no difference. That's very blunt, I know, but that's the null hypothesis. It's not the conclusion we're going to come to. We will not come to that conclusion because we can't. We cannot just simply say in the conclusion that there is no difference in birth weights. But in terms of the null hypothesis, nothing to see here. Innocent until proven guilty. You did not commit that murder. Null hypothesis is nothing going on. No difference. How I express that? Well, there's a number of ways to express that. But what I'm going to write here is probably the most common way. That is probably the most common way of showing that there is no difference between the two. Let me see. Piece of 1. I'll put near 9/11, and P sub 2 not near 9/11. I need to indicate which one's which. My alternate hypothesis is based on the question. The question up top is saying, okay, do we have evidence to show that there were more babies with low birth weight near 9/11 site? Were there more babies born with low birth weights near the 9/11 site as opposed to not near? So the alternate hypothesis is the same calculation, but this time I'm showing an alternative of it being greater than 0. Now again, you can go greater than, you can go less than, you can go not equal to, but that depends on what the question is asking. If the question was asking, is there a difference between the two, then I would put something like not equal to. But since it's just saying, okay, they're specifically saying, we think there are more low birth weights of babies born near the 9/11 site as opposed to not near. So if that's the question that's being asked, I'm going to be, okay, well, the difference here, because this is near it, this is not near it, I'm going to say greater than 0. Again, number of ways to kind of express that. You could also, for your null hypothesis, you could literally say P sub 1 equals P sub 2. You could also do that. P sub 1 equals P sub 2. You could also do P sub 1 for the alternative. You could do P sub 1 is greater than P sub 2. You could also do that. There's a number of different ways to go about this. In fact, we may need to know that information when we type this junk into our calculator. But we'll get there. Oh, we will get there. So, assumptions and conditions. Come here, paper. Here we go. We need to hit these assumptions and conditions. Assump, condish. So let me just kind of label these out for the sake of time. We talked about them before. Random samples stated for both. It said it in the problem that they were random samples. Let's see, 182 and 2300 are large enough samples. I'm going to do these two separately, but 182 is less than 10% of all babies born near 9/11 site. Because again, these are two separate things because it's either you're born near it or you're not born near it. 2300 is less than 10% of all babies born not near 9/11 site. There we go. And again, the assumptions and conditions are probably going to be the most tedious part of this whole thing. But you need to list them out. You need to list them out. An AP grader is going to be checking that you hit all of the proper assumptions and conditions. Let's see. Now, again, we can't do expected successes and failures because there is no expected. I've already done these calculations, so I already have them written down to make it a little bit easier. Well, 182 times 0.08. We can't do expected successes, but we can do observed. This equals 14.56, which is greater than 10. Observed successes, 182 times 0.92, which is 167.44. I'm going to move this up to the top and zoom in. There we go. For observed, I just put OBS. That's greater than 10 observed failures. 2,300 times 0.04 is 92, which is greater than 10 observed successes. And 2,300 times 0.96 is equal to 2208, which is greater than 10 observed failures. Again, it seems like why do we have to list out all of this junk? It's what's expected of you. What is expected of you is that you hit upon all of the assumptions conditions. Now, I'm going to talk about independence in a moment. And the feasibility of that, clearly. But I just want to make sure we have that written down. There's two different types of independence that you can talk about here. Two different types. You could say independence, feasible for birth weights in babies. And we can assume that based on everything that we just did, less than 10%, large enough, random sample, these successes and failures, things like that. But also, this is another type of independence. Yes, we can assume independence between birth weights and babies, but there is also independence between the two samples, meaning one sample did not affect the other sample. Making sure I have all the proper information here. Heck yeah. Okay. Based on all of that, based on the fact that we have categorical data, based on the fact that we have two samples, and based on the fact that all of the assumptions and conditions that we needed were hit, we are going to be using a 2 prop Z test. Now, I'm going to go into the details as to how we actually conduct that test with normal CDF next time. I'm going to have to get into that next time. And I'm going to do it with this birth weight example. Today, I'm going to use the calculator to get this thing done. But be forewarned, I need to show you the inner workings as to how they actually calculated the normal CDF, because those inner workings are going to heavily affect the way that you answer certain multiple choice questions. Trust me on that. It's going to be insane. Quick preview of that, quick verbal preview of that. How do we combine two standard deviations? This is going back a few chapters. How do we combine two independent standard deviations through addition or subtraction? That wasn't a question. Addition or subtraction. Those were the operations that you could, potentially, that they're asking you to do. Because you can't just add them together. You can't just subtract them. What do you got to do? What do you call it when you square standard deviation? Oh, it's silence. Do you know? Say again? Variance. Same concept. If you're going to be doing a 2 proportion Z-test by hand using normal CDF, and you need to combine the two standard deviations by subtraction, you would have to square it to variance, add them together regardless, and then square root them back. Oh, that's not for today, though. Today, we're going to do this. Today, I'm going to let x1 equal 92. No, not 92. I apologize. I'm going to let it equal 15. There we go. And I'm going to let n1 equal 182. I'm going to let x1 equal 92. And I'm going to let n2 equal 2300. Now, where the heck did those numbers come from? Well, the first sample were babies born near the 9/11 site. And there were 182 in that sample. And we calculated the observed successes, in which we had 14 point something, right? What was it, 14 point something? 14 point? Yeah. I can't put a decimal into the z-test. I can't do it. So I had to round that to 15. These were the babies not born near the 9/11 site, and there were 92 observed successes. That was the 0.04, the 4%. Okay. Let's see what we got here. Oh, I got to do one more. P sub 1 greater than P sub 2. I'm going to go to my calculator on my computer. I'm going to go to the calculator on my computer just so I can see the exact same interface that you would typically see. Come on. Come on, Smart View. Load faster. There we go. Stat. Tests. 2 prop Z test. 15, 182, 92, 2300. P sub 1 is greater than P sub 2. You can calculate or you can draw it. I'm just going to calculate. You can draw it if you want, but calculate. And you get this information here. Now, all of these hats, just to be very clear, all of these hats. P sub 1 is babies born near the 9/11 site. Obviously, it was a little bit more than 8% because we had to round. The P sub 2 was exactly 4% because we didn't have to round. Then there's this P hat. What? There's an extra P hat. Whew. This is what they called, and this is going to be something that's going to affect us in the future. This is actually something that they called a pooled, like a swimming pool, a pooled proportion, where they actually combine the previous two proportions. There are reasons for that, but we do not have to worry about that at the moment. We don't. What we're really interested in is this one right here. This is your P value. This is your P value. This is the probability of seeing these types of results given those sample sizes. That's the probability of seeing such sampled results, assuming that there is no difference between the two. So I need to write that junk down. Let's see, it was 0.0033. My P value was approximately 0.0033. I can't see it. There we go. It was approximately 0.0033. Now, what that means is this. Now, we didn't actually set an alpha level, but let's just assume it was 0.05. Conclusion. At the alpha equal 0.05 level, what do? Are we rejecting or failing to reject? When do we kick the hoe to the curb? And the P is low. Is it low enough? Yeah, heck yeah. We reject the null hypothesis. There is evidence, I'll move this up, there is evidence to suggest, get to my next page here we go. There is evidence to suggest the low birth weight rate for those born near the 9/11 site is significantly higher than those born not near 9/11 site. Finally, just again to kind of reiterate the fluffy language with the conclusion, it appears. I'm not saying it is, I'm not saying it's absolutely definite, but I'm saying it appears the debris of 9/11 has negatively affected birth weight in babies. That's my conclusion. Make sure you have that written down. I'm going to leave that up on the screen for a little bit. I can repeat whatever you need, but the bell's going to be ringing in about 15 seconds or so, and I'm going to call it a day from there. If you have not left a comment in the chat, please make sure that you do, and we will bid you adieu. Thank you, you too. Okay, see you guys. Bye. See you. Bye-bye. Have a good one. Man, that thing keeps dropping on you. See you guys. See you. See you. Bye. I gotta start this next thing. Oh, I never turned off the light screen. Great. Have a great day. Dude. Everyone's also like chipper. I'm like, I talked about low birth weight in babies during 9/11. Everyone's like, see ya. Have a good day. Okay, guys.
Have a good day, Mr. Mark.
See ya.